Good morning, friends. Yeah, this is the first class. We're going to look at what is a system on a chip. So it's extremely important to understand. So this how the VLSI and embedded system, they are misnomers. What the industry designs is chips. We put entire system on a chip. So this is what we'll see. What is a system on a chip? So it's basically a collection of components. If you look at if you know what is a printed circuit board or a PCB, it contains various discrete components connected together using wires. Or if you look at breadboard, you are all familiar with breadboard. So all the discrete components connected with the jumper wires, and you connect your signal generator and use a CRO or a logic analyzer to monitor the output. Right? Same way, whatever is a printed circuit board or your motherboard is going into system on a chip. So it's basically, I'll not read the slides, I'll just tell the concepts, you can walk through the slides. So it integrates all the components into a one particular area, into a single chip, right? So there's a system on a chip. So it could contain digital, analog, mixed signal, or a radio frequency components, right? So that's on a single chip, that's called a system on a chip. This all data is taken from Wikipedia, right? So example is a mobile phone is a very good example for a system on a chip. Mobile phone has a Snapdragon processor from Qualcomm. It has a CPU, it has a graphics processor, it has a modem, it has a peripherals like interrupt controller, UART, USB, right? And you have a SD card where you put your external memory, and it have a touch screen interface, LCD interface, right? So it has several interfaces. So it has a lot. We'll see in the next slide. We'll see more details. So it will have analog to, you must have read about analog to digital converters or digital to analog converters. The converters, so the chip will have those kind of components also. And it will have memory, internal memories, with SRAM, ROM, those kind of components will be there, and there will be inputs and outputs for the chip. Right? So system, what is what we meant system? System refers to the hardware and software. It is basically analog components, digital components, some storage and software. So these are typical four components in a system, plus the PCB, as I said, the printed circuit board. So inside the chip, we'll have the periphery will have mixed signal components, analog to digital converters, digital to analog converters, phase lock loops, also called PLL, and some radio frequency components will be there. For example, with a modem or a Wi-Fi has to talk to the external world to your cell phone. So we need a radio frequency components that also will be part of the chip. And digital components, typically a microprocessor or a CPU, will have interfaces like a SPI, I2C, UART, USB, PCI. There are different interfaces, right? There are several accelerators. They told GPU. Right? We all play games in the mobile phone. It needs a lot of 2D graphics and 3D graphics. 2D graphics for the display of the user interface, but 3D graphics is for playing games. We have camera, to capture images or take video. There are accelerators for the camera, for video encoding and decoding. There are digital signal processor for acceleration. A lot of hardware is basically acceleration. Whatever you cannot do in software in real time, they all go into the hardware, right? And there are storage components like SRAM, flash, ROM. They're all inbuilt. DRAM is typically not put inside the SoC. The technologies are developing. People do like stack die, and there are new technologies coming like 3D ASIC. There are several things are coming up. So the DRAM also will become part of the chip in near future, or it's almost a trend in the industry. I'm not actually aware. If you have questions, I can get answers for you. And software is part of the chip. So that's why I said there is nothing like VLSI or embedded system. The training institutes and academic is fooling people. What we design is system on a chip. So system contains both the hardware and the software, right? So embedded software is so system software is operating system, right? You have right application software. Your IT is also part of the system. The cloud, everything is part of the system. I'll make a separate diagram and show if there is an interest. So real-time operating system, right? So we have embedded Linux, for example, right? And we have an IP device driver. We have a microcode or a device driver for a I2C or SPI. So that's an example. And there are several applications under the software, right? So device driver is the called board support package, or we run a microcode on a ARM9 processor, right? Or it can be on any processor. It can be a PIC microcontroller, for example. You can use that also. And application software is all running on top of the board support package or real-time operating system, where you have several layers. Will not go into that. Example, uh, like your games and various layers. We have APIs. We can Android, the operating system. We have application on top of Android. Your phones, we have various applications, right? Gmail is one application. YouTube is one application. Ola, Uber is one application. Donzo is one application. Porter is one app. There are many apps, right? That's example for the apps. So we'll see example for SOC. So we say ARM processor, or it can be any processor. ARM is a major choice, and today's latest trend is a RISC processor, and RISC 5, the latest trend. But you can have any custom processor there, whatever you can have PIC controller also. Depends on your need of your application need. In this example, what is the Wikipedia? We're looking at ARM processor example. And so there are a bunch of peripherals. We spoke peripherals. We see Ethernet. We all know what is the Ethernet. Ethernet is a peripheral. Your UART, SPI, serial peripheral interface, and the two-wire interface like I2C, ADC, DACs. CAN is for a very popular interface for the automotive. CAN interfaces. USB device. USB device is again good, very good example to communicate with the external world. We all know what is USB, plug and play, right? I don't have to explain, right? And the pulse width modulators and serial controllers and timers, counters. These are various peripherals what we have. And as we said, we have memory, SRAM and flash memory and ROM, right? And there's a memory controller to talk to SRAM. And external bus interface will talk to the DRAM, which is outside the chip. It's called EBI, external bus interface. So typically we have a LPDDR, that's industry standard, LPDDR5, LPDDR6, and comes the high density, right? Low power. That's the latest trend in the industry. This is an outdated diagram. So we have a controller layer, physical layer, and then the actual device actually sitting on the board. So people write models and they integrate that, associate, and verify that. We'll see that later, right? And system controllers are there, right? For which talks to the processor. The interrupt controller, PLL, and oscillators, which gives a reference clock to the PLL, RC oscillators, right? And there are various components. Will not go watchdog timers. Each of them can be a separate topic. This is giving you an overview for that, right? It's going to be just 45 to 50-minute lecture. JTAG is called Joint Test Action Group. So JTAG is very important to test the components inside the chip and components in your PCB. That's is for scanning all the flip-flops. That's very interesting topic. We could see that in the detail later in the separate videos later on. JTAG is very, very important component. There are IEEE standards for that. So there's something called internal scan, external scan. What is a scan? We do a scan when you go to a doctor. They will try, I want to scan your abdomen. I want to scan your chest, brain scan, MRI scan. There's anything, right? What do you so it scans, right? So when you say scan, you want to scan a textbook. You put use some scan app in your mobile. You scan that into PDF or JPEG, right? So it's going to scan the contents of the flip flop or scan the input and output of the chip. So we call primary input output, right? So scan can either internal scan or external scan. The details we see in the subsequent videos. So what is the design flow for a system on a chip? How do we design that? So the spec is the starting point. So we need a spec. All right. So I don't think we can zoom here. Let me try. Oops. I don't think I zoomed. Okay. So let's look at this diagram. I think I lost the previous slide. I think I use a pointer or something. Don't to zoom. I don't know how to zoom. Okay, here. Okay. So specification is the starting point. Initial starting point, the product, like what a customer want. We all design the services or the turnkey projects or a chip design is driven by the customer. The customer data is very important, right? The market survey, what we call in industry. The product and marketing requirement, PRD document, what we call product and requirement document. That is driven by the marketing and sales team, right? So you take that from their architecture team, prepares a specification document. The specification document, based on that, we do system architecture. What is going to software, what is going to the hardware. So we prepare that, right? So that's the system. That's a system specification. From the specification, we write a system level specification. From there, we write what components are going to software, what components are going to hardware, and then prepare the chip system architecture. Then based on that, do the software architecture separately and hardware architecture separately. The software and hardware, they work co-work. So software can be either embedded software or a system software or anything. So there are many things. So software and hardware has to start right from the beginning. I always tell it's like a husband and wife or like a bullock cart. You need two bullocks to take the bullock cart. One bullock cannot drive to take the load. We need both father and mother in the family. Without that, the family is not complete. The children will suffer, right? So husband and wife are two bodies but one soul, right? So that's what. So don't ask me who is software, who is hardware. That's a trade-off, no, between the husband and wife. Anybody can play any role, right? But they are one soul. So SOC is the soul, right? So hardware can be a husband or a wife. It's up to the between the husband, between the family, what role they want to play, right? So we'll look from the hardware point of view now. From the hardware spec, we write something called a microarchitecture. So what are the various blocks? We saw in the previous slides, there is CPU, there is a peripherals, and we saw a bus interface, and IOs, JTAG, and all this, right? So that's a microarchitecture block level diagram we prepare, right? So from the microarchitecture, that's a basic reference. We do a verification and test plan. How do we verify the design? This is extremely important. This takes most of the time in the design life cycle. Typically 60 to 70% of the tape out cycle, the verification takes. So it's crucial because if you miss any bugs, it's expensive. The cost is it goes to scale of 10. The block level verification, subsystem level verification, system level verification, and post-silicon verification, testing. So everywhere the cost increases by a factor of 10. So the verification plan is extremely important, test plan is important. There's a separate team, there's a design team, there's a verification team. They work again like husband and wife, they have to work together. And verification team should work like a software. They should work, take the hardware like a, they should not go, they should treat the SOC as a black box. There are different levels of verification, black box, white box. Typically, we should treat that as a black box. The verification should work like a piece of device driver. Right? That's extremely important component. So once the microarchitecture is done, we'll do a design review. Reviews are very important. Every stage there are reviews. For example, you buy a product on Amazon. What do? You do a review, read the reviews. Some reviews are biased, some reviews are neutral. You can make it out. Or you could go for any gadget, NDTV gadgets or third-party reviews you can review. Right? Or you ask your friends. So that's it. So similarly, in the design part of the process, we do design review. So microarchitecture and there's a design review. So once the design review is done, then we take the feedback. There's a feedback that is not shown in the diagram. So the feedback goes all the who does the review? Your peers, your subordinates, your supervisors, the directors, the team leads, managers, everyone. They do the design review, and the feedback goes back to microarchitecture. They update the architecture document. Similarly, the verification review is done with our test plan. The feedback goes back and it's a loop. You go and update the verification plan. So once the reviews are done, you actually start the coding. RTL coding. RTL stands for Register Transfer Logic. It can be Verilog, it can be System Verilog, or it can be high-level verification language. There are a lot of languages, System C and Blue Spec. You can use those kind of very high-level language. You can, for example, FPGAs, you can write the code in C. You can write directly implement in the FPGAs. So we can do separate things based on people's interest. It's a huge topic. And after 30 years of experience in the industry, I'm not mastered. I'm learning every day. So that's the thing we have to remember, keep in mind. Learning. That's the bottom line. Quality. No compromise. And time is important. We have to deliver on time. If you have a class, you have a meeting at 11 a.m., you have to be there 10 minutes before. That's the discipline we should have, right? So industry is all about beg, borrow, and steal. You have to get it done. Whatever it means, you don't care. Quality and time are utmost important, right? So the RTL coding is done in parallel. They do the verification environment development, test cases. Typically, we use a system Verilog and UVM. Now we have Coco TB. There are a lot of languages. Based on that, we do verification, right? So once this is done, we do design review. There are various reviews, right? High-level design review, mid-level design review, low-level design reviews, right? This is a code review which happens, right? And verification also gets reviewed. So during design reviews, verification team is part of the design reviews. We do the verification review. Design leads are part of the verification reviews, right? So when you do the STL coding, there are a lot of IPs which are reused from the previous projects, or you buy a third-party IP. For example, ARM. ARM processor IPs are third-party IP, which you have to pay royalties and buy the IP. RISC-V processor, they are free. You can buy from the, you can download, for example, Shakti processor. You can download from the Shakti website, and you can, Dr. Kamakodi's brainchild, Shakti and Maushik processor, you can download and integrate with the design and do whatever you want. We can develop an entire SOC, and we can tape out SOC for free. We'll talk about that in the upcoming classes about that. And video design reviews. So what are the how so when you code RTL, what are the tools are integral part of the design process? Extremely important. But tools are not only one thing. Artificial intelligence, people call. A lot of hype. We believe in natural intelligence, NI. Please write down NI. Tools are just like slaves. You are the master. You know, JK flip flop, right? Master flip flop and slave flip flop. Very similar to that, right? The user is a master. AI is just a tool. NI is a what we have. The nature has given a brain. All the students have the same brain, but you don't have believe in yourself. That's why we say unleash the human in you. That's the tagline what we use it. Every human being in the world has the same brain. Only thing you are not trained. AI is your training. AI is not mature, right? You have to train. So like if you know neural networks, you have to train it, right? If you know what is a DDR, you have to train it. LPDDR, you have to train it. Very similar. You have to train your brain. Students in Stanford, MIT, Berkeley, Massachusetts, wherever they are, or people in India, even IITs, NITs, triple ITs, VITs, rural colleges, doesn't matter. You all have same brain. There are untrained brains. The academic people train you unnecessarily. You go to industry people, the industry, they will train you what industry needs, right? Academic people, they untrain you. They don't know how what industry needs. I have a lot of respect for academic, so please don't think I'm enemy of. I have academic research oriented. They are extremely good at writing papers, patterns, and research algorithms. I have a lot of respect for them, right? But on industry is all execution, making products which complementing, right? Academic industry should work together. That's why we call bridging the gap between campus and corporate. We believe in bridging. Campus has a strength, corporate has a strength. We have to co-work, right? So the coming to the tool flows. So we have various tool flows. So lint. So I will not go into details. There is something called lint. It checks an upfront whether it's like you can go to Google and search, or you can ask ChatGPT what is a lint. Right? These are learning areas for your own. It takes the RTL as input. It takes certain constraint as inputs. Takes certain policies as input. It checks the RTL list can be converted. Is it testable? Is it low power friendly? Is it can be synthesizable? Is the coding guidelines is correct or not? So it checks so three, four things it checks, right? If you have any questions, you can ask. I have made other videos. I'll start my presentations in public. Please, make a comment on the YouTube video. We'll share the more details. Clock domain crossing. It's a very, very detailed subject. We'll not touch that. The SOC has hundreds of clocks. Minimum small SOC will have. I have worked in SOC which are minimum 500 clocks, 800 clocks. Right? Extremely important to understand. It's a huge, huge topic. We'll not touch that. Right? Synthesis is a process where you convert RTL or a Verilog code or a system Verilog code into a gate level logic. Right? That's process called synthesis. The synthesis has inputs, technology libraries as inputs. We call 45 nanometer, 28 nanometer, 4 nanometers today's trend. They're going to talk about 3 nanometer and 2 nanometer. Right? Beyond that, they'll go to femto and pico, right? Nanometer, then femtometer and picometer, right? That's what industry is going towards. It will scale. Moore's law will never die. Gordon Moore is no more, but Moore's law is always valid. That's what I believe in. My NI believes in that, right? If it is not valid, somebody can research and prove, I'll accept it. Please show me research papers. So synthesis will convert, it takes the library as an input, it takes constraints as an input. Any tool doesn't know, right? You have to constrain the tool. For example, human brain is unconstrained. You just sit in a corner, keep quiet for 10 minutes, just close your eyes and sit. Whatever it is name you call, sit for 10 minutes, close your eyes. Your mind will go in all directions. But if you tell your brain, think about this particular aspect, what book you read before, what movie you saw previous day, what you food ate in the previous night. Just think about it, sit, your brain will be focused. We call power of focus. We can talk about that if you're interested. The power of focus, the very, very important thing. So you have to constrain your brain. So your unconstrained mind is very, very dangerous, right? That's why people like terrorists and or religious extremists are there, right? You have to be stay in the middle. You cannot go to extremist, either religion or a terrorist, right? We are not here to talk about religion here anyway, right? It's education. Education is irrespective of religion, caste, creed, right? So synthesis converts, you put a constraint, you put a technology library, then you get a netlist out. The netlist is a collection of gates, flip-flops, and the connection connecting the same. We call them netlist, Netlist, netlist. That contains a connection of gates and flip-flops. That's what the synthesis tool provides, right? So then we do something called formal verification. There are two types of formal verification. We'll talk about what is the commonly used in the industry today to check the RTL, which we use generated in the previous slide. Is it correctly mapped by the synthesis tool? So formal verification takes a constraints as input, RTL code as input. It takes a netlist from the synthesis as input. It checks and they're checking it's equivalent or non-equivalent. That is formal verification. There is one more formal verification, part of the verification flow, which is outside the scope of this discussion. That's all advanced topics. We'll not talk about it, right? And there is something called low power verification, which is static verification. You generate a file called UPF, Unified Power Format. You have to write that based on your power specification. If you have power islands, if you want to care about power collapse, it's again advanced concept. We'll talk separately. So low power verification is for the tool flows. Again, you give a UPF files, you constraints. Then low power verification tells the UPF policies are met or something is violated. You get a lot of reports. You have to analyze that. There are a lot of industry tools available for that, right? Then what we do is design review. Tools will give you thousands of logs, thousands of logs. That's why you should know scripts, Python or Perl, Tickle, Unix scripting. Scripting is extremely important. Ubuntu is very important. Don't work on Windows. If you're working on Windows, you're not industry ready. You have to work on Ubuntu Linux. It's free. You can download, I don't know what is the version 21, 22, 25. You can download, it's free for all. Don't remove the Windows partition, install the Linux partition. Then only you can take my classes. There is something called design for test. So scan and the memory best, right? So it will be a separate topic. That will be a focus of this particular course. We are going to talk about design for test. So scan and memory best, we have to check the design is testable or not. You don't have manufacturing defects, right? You have defects. You buy your phone, you use it. After 1 year, the phone hangs. What do? You go back to the showroom. You have warranty. Go and give the phone. You apply some patches, or you take back the phone, gives a new phone if you are in warranty, right? So we have to catch. So what when you give back the phone, what does the industry do? Who design the chip? They have to find out where is the defect. They have to repair the defect, or they have to find out what is the reliability of that, right? So for automotive industry, it's extremely important. The reliability is extremely important. So the design for test is going. We are going to talk in detail about design for test in the next video. It's going to talk about the scan, memory based, logic based, compression, and a lot of other advanced topics we're going to talk. So once you do a design for test, that comes after the synthesis, then do something called physical design. Physical design has a bunch of process. We'll see in the next slide, right? So that's an important process where you convert your netlist into a GDS2 format. I do not remember what is the GDS stands for. You can Google GDS and Roman numeral 2. You can look at what is it, some format which the foundry will accept that they'll make the better layers and mask layers and they fabricate the chip. So physical design is a process which converts your netlist into the GDS format. So it takes a netlist and converts into transistors and metal layers and make the connections appropriately, right? Signal connectivity, metal connectivity, power connectivity, everything the physical design does, which we'll see in the next slide, right? So verification is happening in parallel. That's why I showed you here in parallel. RTL simulation. So it takes the RTL, take the test bench what we spoke in the previous slide. You run simulations. A lot of automation is needed there. That's why again Perl, there's assertions, there's advanced topic. That's a separate course by itself. This is only an overview thing, right? So this is extremely important to do that. You run simulation, debugging simulation, extremely important. Believe me, this is a challenge, most challenging job. If you can do this, you get a job in industry. How do you learn that? I don't know. I do not know. It comes with experience. You write one RTL, take a simple 4-bit counter, you write RTL, write a test bench, simulate it, you'll know. You take any design, you code any design, verify that it comes with experience. So debug is the mantra. Silicon debug, post-silicon debug, FPGA emulation debug, 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 bug and debug. That's like husband and wife. You have a bug, you have to debug, right? Analytical skills, right? Extremely important. You know what is analytical skills? They do a test, right? If you have good aptitude and analytical skills, you can do anything. You can become number one in the SOC designs. Please write down, underline my word. There is no recession. People talk about recession. When the recession went, it's all bullshit. I'm sorry to use such word. There is no recession if you have the right knowledge. There are jobs, but people are not knowledgeable. College or all the academic is unlearning you. You have to unlearn what our academic is teaching you. With due respect to an academic, right? So this is extremely important. Then the reviews are happening. So all the tools will provide thousands of logs, tons of thousands of logs. You have to review each warning, each error, each info. You have to review that. That's your job. That's where you're paid for. AI cannot do it. AI can run the tools, but maybe you can use AI to automate some of that. AI is only a tool. It will not replace your job. It is going to create more jobs. So do not worry. AI will die natural death after 5 years. New technology will come. But basics, AND gate, OR gate, flip flops will remain same forever. Right? Your digital design, CPU design is very important. They will never change forever. Then we do a coverage analysis, which is outside the scope of this thing. How do we know your verification is complete? There's something called functional coverage and code coverage. Please write down that. We'll not talk about the detail. On FPGA emulation, before you send your silicon, we have to verify that it works in real time with the software. So you use something called FPGA, which is field programmable gate arrays. Use that and verify that in FPGAs. And you verify that, right? So once you verify the FPGA, so we do a gate level simulation, which can be pre-layout or post-layout based on the FPGA or ASIC. Pre-layout is something with the netlist what you get from synthesis. Do a pre-layout simulation. Post-layout is something which you do after the physical design, either after your floor plan, after your placement, or after your routing. There are various stages of layout. We'll talk about the next slide. So based on that, we do the simulations. So we go to something called annotated simulation, delay annotated simulation, or with the actual timing data. Right? What is timing? Your college will not teach. You should know what is setup time, hold time. That's part of your digital logic design. The college professor don't teach. Please ask us in industry. Please please write in LinkedIn. Please comment on this YouTube video. We'll answer. Right. So FPGA simulation emulations for pre-silicon validation and for pre-silicon software bring the software on the FPGAs. You emulate everything in a specific hardware. Make sure that your design is working properly before the tape out. And you do a lot of reviews, right? So when your reviews are extremely important, don't bypass any reviews. Let's see what the next slide shows for. So physical design, let's talk briefly, 5 minutes on that, right? So physical design consists of floor plan. What is a floor plan? If you're buying a house or you're building a house, you decide where is the living room comes, where is the bedroom comes, where is the study room comes, where is the puja room if you believe in God. If you're atheist, you convert it as a storeroom. There's a kitchen, there are toilets, there's a balcony. Whatever you want. You want wooden flooring, you want a false ceiling, where the lighting looks like, all those things. That's like similar like a floor plan. That's the example. What block goes there? Where does the memory go? Where does the PLL sit? Where does the standard cell logic sit? Gates and flip-flops. That's a floor plan, right? Then the placement. Once you design a floor plan, how the logics are placed. That's called placement, right? Then the clocks are built. There are so many clocks that chip, hundreds of clocks. You have to do something called clock tree synthesis. Clock routing. So clock routing should have less skew. If you know what is setup time, hold time, you will understand what is a skew. There are important concepts that college should teach. Prerequisite for any chip design course, VLSI course, what you call, right? So clock tree synthesis, right? Extremely important. Routing. So once the clock is made, then route signals are routed. Once the signals are connected, you get the RC. You can backward RC. What is RC? It's resistor and capacitor. So you back connect that, you get the actual delays. You can optimize that the routing. You get the based on your constraints, all these things work. Then there's something called ECO, engineering change order. You can change the functionality anytime, and there can be timing ECOs, which is outside the scope of this presentation anyway. So we want to change the design function. Let's say your chip is already almost ready for tape out. You want to add one AND gate. Your verification says that it finds a bug. You bug and you debug, you found there's one AND gate should be added somewhere. So you do something called a functional ECO. You add a gate wherever you want. You connect the metals appropriately. You don't have to redo the synthesis. You can insert that particular component wherever you want. You complete your ECO. Similarly, there are timing ECOs. There's something called static timing analysis. Extremely important topic. STA, what we call STA, static timing analysis. So you should know what is the setup time, what is the hold time, what is the reset to removal time, recovery time, and everything. You should know all those things. Then you could do the static timing analysis. The separate topic outside the scope. You check the design will work or not. There are something called PVT, process, voltage, and temperature. There are different something what we call as corners. You know what is a boundary condition, right? You want to catch a train or a flight or a bus, which is at 2 p.m. So you have to leave before, well before. Let's say you live in traffic, say like a NCR region or Bangalore or Hyderabad. There's a lot of traffic. In villages are becoming, today there's a lot of traffic. So we want to catch a train, you have to plan. Let's say due to unplanned traffic, what happens? You go in the last minute. The flight gate is almost going to go, or train is about to take off. You run and get into the last compartment, then you walk through the vestibule, right? That's called corner conditions. So static analysis does all those things for you. It checks the design is going to work across process, across temperature, across various conditions. That's what job of the static STA. You do physical verification, right? We do something called RTL to GDS2. Physical verification is extremely important, which is outside the scope. Then we do tape out, base tape out and metal tape out. There are various layers in a chip. If you look at a PCB, if you understand what is a PCB, you can understand what is a chip. There are two-layer PCBs, four-layer PCBs, multi-layer PCBs are there. Similarly, here you have base layers and metal layers, right? Various layers are taped out, and you write GDS and send it to the fabrication house. Something like TSMC, UMC. In India, Vedanta is coming up, right? Foxconn is coming up. There are many people are working on. I know many other names, but I cannot talk in public. Fabrication plants are coming in Gujarat. Micron announced a packaging plant. So once you fabricate, you get wafers. From wafers consists of a lot of dies. Wafer is circular in nature typically, and you have a lot of dies. Not die, D-I-E die, not D-Y-E, D-I-E die. It's not death. The actual silicon is called DIE. I don't know why they call die. Because you perform or perish industry, right? If you do your job, you'll get fired. You'll get a lot of money if you do well. If you don't do well, you'll be shown the door. You have to go home and sleep, right? Maybe that's why they call it a die. I'm just joking, right? But you'll do well. So packaging. So you have to create a, you have seen a package. Through IC, it will be black in color. There's a DIP pack, 74LS00. 74LS04 is an which is inverter. 74LS00 is an AND gate. If you look at that, it's called dual in package. There are 8 pins, 12 pins, and things like that, right? You can search in Google, use ChatGPT to learn. But ChatGPT will give wrong answers to you. Don't believe ChatGPT. You believe in NI, not in AI. If you have a question, post a video on our YouTube channel. One of our partner will respond. Everything is done. You do a final review. It tapes out. Then your senior VP actually signs the check. Then you pay the money to the foundry. Then you are committed. Any mistake happens, you are not responsible. You are to your time to market, your money, everything is important. Everything is gone, right? And once the chip is taped out, you work on ATE test vector. ATE is automatic test equipments. This is the focus of this particular course. We'll keep seeing about ATE. We'll talk in detail. Automatic test equipments. We generate various vectors using the DFT. We memory based vectors, scan vectors, compression vectors, functional vectors, mixed signal vectors. All those vectors we develop and keep it ready. So when the chip comes back from the fab, either on the wafer, on the die, on a package part, we run all these vectors, and using the ATE machines, we check the chip die is working or not, whether a wafer is working or not, whether the package part is working or not. So you do that automatically. That is part of the ATE. So post silicon process, what happens? Quickly, very high level. So silicon on dock, where the silicon comes from the fabrication unit. From after packaging, it comes to your company. Then you do all the testing using ATE. And there are a lot of testing teams called validation team, test teams, n number of teams to take it to the customer sample, to take it to the customer, right? So you do a lot of validation, software bring up, board validation, software bring up. Everything happens in parallel. We call PVT, right? Process, voltage, and temperature. Software and hardware, we have to test together and do that. System performance test, SPT. It's a very advanced topic. We'll not talk about it. Extremely crucial. System where the software and hardware put to a extremely stress situation and they're tested, right? Then do something called engineering sample, where you give basic samples, do reviews, then you give the product to your OEMs or your things, then they use that and test the particular chip. Then you do something called correlation. What do you estimate initially during architecture phase or in your simulation phase or in the your pre-silicon phase and post-silicon? You have to correlate all the data. Whatever data you get from ATE, system performance test, the validation test or software test, you correlate all the data, minimum voltage, minimum power, performance, everything you correlate. Once everything is done, we do customer sampling. We do reviews. This is the final review, CS review, what you call customer sample. Once this is done, the product go in mass production. You make billions of product. There's something called NRE. We'll talk about it in detail. We'll talk about what is a test. We'll talk about NRE, right? So customer sampling happens, and the customer actually gets a sample. They go to bulk production. Typically, during December, Thanksgiving weekdays, your production happens. Chips or phones are launched. So what is benefit of SOC? I'll not read. The slides will be provided to you. You can the YouTube video will have a slide reference. You could walk through that and you can see that, right? It includes overall reduce system cost, increases the performance, low power, reduces size. Yeah, these are all theoretic part. You can Google and you can read our own or you can self-reading aspects. What are the challenges? Let me spend a minute. I'm going to stop here. Extremely complex, right? Use ChatGPT, use AI, it doesn't matter. NI is important. I believe NI, your debugging skills. This is what academic doesn't teach you. You have to talk to industry experts. Don't go to internships industry. They will fool you. Do the project within the campus. Industry people will come to the campus and will help you. That's what bridging the gap between campus and corporate. Do not take internships. It helps, but majority of them doesn't help because you run scripts. It's like LKG. Internship is like LKG, but you'll not learn everything. You want to learn actual thing, go to startup companies. Work on startup. You get startup companies will come to the campus. You can set up startup companies in the campus. The government of India is allowing. There's a lot of semiconductor India mission, right? That's extremely important. So that's helping that, right? Complex of silicon is huge. Process is scaling. We said 40 nanometer, 28, 12 nanometer, 10 nanometer, 8 nanometer, 4 nanometer, and beyond. Femto and Pico, we spoke about, right? Scaling. Extremely important. New materials, not just silicon. We have various, we'll not talk about that. There are various researches going on. A lot of materials are used. Your architecture are getting complex. Performance requirements are increasing. Power management is getting complex. Verification challenges and everything, right? So that's pretty much tools methodologies. Yeah, it's all self-reading. I'll stop it now. Any questions, please comment on the video. Yeah, so we will answer the questions on the YouTube video, right? Thank you, subs. Thank you. Wish you all the best. Please subscribe to VLSI Design Class YouTube channel. We plan to put more videos there. Wish you all the best. Bye bye.